Since the Industrial Revolution up to the present, fossil fuels that made our lives bountiful. Although the current issue is how to develop a renewable energy, Korea's energy power policy still focus on the established stable economic energy so far. As coal-fired power plants ideal for the purpose are successively built, one important challenge is to address the environmental and social issues following national mid- and long-term energy planning. KIGAM, the Korea Institute of Geoscience and Mineral Resources and NIIL Cement have studied how to recycle the byproducts from thermal power plants as resources. They developed a new technology for recycling industrial byproducts and reducing carbon dioxide as well to suggest a new potential of energy from fossil fuels. Abnormal weather due to global warming has made the world endeavor to develop new energy, but the world concentrates currently on coal-fired thermal power generation again. What made us return to coal-fired thermal power generation? Since the Fukushima nuclear power plant accident in 2011, concerns about safety of nuclear power and globally stabilized long-term prices of bituminous coal highlight the importance of coal-fired thermal power generation. Global demands for coal-fired thermal power generation technology, as well as the power generation market of Korea, continue to increase. Accordingly, the governments of Korea and other countries strengthen the responsibility of coal-fired power plants for the environment and request them to assume the obligation of reducing greenhouse gases. This team is a leader in developing the high-functional green cement technology for recycling byproducts from thermal power generation, aluminum processing and a water treatment process to convert thermal power generation to clean power generation. The KIGAM and NIIL Cement discovered industrial byproducts the most ideal as a raw material for alumina, and found out the raw material mixing condition for reducing the amount of used limestone and producing substitute material for natural alumina, or is to develop the best synthesis technology for producing low-carbon high-functional green cement. The research team built the Danyang factory of NIIL Cement in 2010 and succeeded in demonstration research based on the developed technology. In 2014, it used industrial byproducts and employed a real cement production process to produce a large volume of high early strength and low shrinkage clinker in a continuous process to commercialize the low-carbon high-functional green cement. This technology is composed of the following steps. The first step is to transfer the crushed and mixed raw material made of byproducts from a coal-fired power plant to the storage tank on the highest floor of the preheat tower. The mixed raw material then experiences a repetitive preheating process by steadily going into the first cyclone to be preheated by the hot air coming into the lower part, and then down to the next cyclone. The raw material of byproducts that went through the preheating process goes into the kiln rotating at a high temperature of approximately 1300 degrees Celsius, is heated and produced as coin-size clinkers. Because the firing temperature is approximately 100 degrees Celsius lower than ordinary systems, energy and expenses are significantly saved. Lastly, the heated round clinker goes through the cooler on the lower floor and then is crushed small to finally become high-functional low-carbon green cement. Because the special cement produced as such features high early strength required for constructing super high-rise structures or emergency repairs, reduced shrinkage for preventing cracks of cement buildings and long service life, and high fluidity for improving workability, it efficiently makes up for the weakness of ordinary cement. Such features contribute to reducing a building construction period to reduce the costs of construction and create new values of byproducts from coal-fired power plants. This technology addresses the issue of securing a site for storage by reducing the absolute volume of burial required for burial sites in a power plant. Because a lot of land is not required in constructing a power plant, the costs of construction are reduced and it is not necessary to comply with all regulations for construction. The technology, which does not need coal burial, contributes to protecting the ecosystem around the power plant and ensures environmental stability for local people. Because the coal-fired power plant is located in the same place for produced byproducts, the costs of transportation are reduced, and the resultant materials can be recycled in various ways. Furthermore, imported bauxite ores are processed as flooring materials for the thermal power plant to achieve economic efficiency and the effects of import substitution. The byproducts from coal-fired power plants can be used as a material to prevent sinkholes which occur from time to time. Other countries have studied how to use fly ash from power plants to fill drifts and pits in abandoned coal mines, and established regulations for recycling fly ash for coal mines. Filling the drifts and pits with fly ash by applying the stabilization technology will help power plants to lessen the burden of the fly ash burial costs, and enhance the safety of the areas around Korea's coal mines and where sinkholes occur. In 2014, the governments of Korea and Australia signed the Korea-Australia Free Trade Agreement and discussed cooperation for energy resources and related manufacturing industry including plants and chemistry. In particular, they paid attention to the energy-saving early strength, low-shrinkage clinker technology to cope with climate change for reducing a large volume of discharged carbon dioxide. They agreed to joint research through the MOU between the KIGAM, the Australian government and the SMI of Queensland University to develop the clinker technology as technology for next-generation greenhouse gas emission trading. They discussed technology transferred for recycling the large volume of byproducts from the aluminum production process in Australia, and cooperation for investment in development, construction, finance and human resource training. The KIGAM, representing the Korean government, and Hanil Cement as a private enterprise, held the Third Korea-Papua New Guinea Joint Committee on Resources, following the FTA with Australia. PNG, Papua New Guinea has abundant natural minerals, for example, copper, gold, silver and natural gases. In the first Korea-Papua New Guinea Forum on Trade and Investment, both the KIGAM and Hanil Cement received a proposal for the ODA project from the Ministry of Investment of PNG. They have a plan to carry out the mineral development project in PNG. Technology for recycling byproducts can change people's recognition about thermal power generation to clean energy, and will contribute to creating added value through efficient demand and supply of national energy and substitute resources. They will develop technology for using byproducts from coal-fired power plants, including plants, and carbon dioxide substitute resources and construction technology. This can be implemented through the Industry University Research Institute cooperation, in securing a business model of creative economy and innovative national energy technology by means of energy resource R&D. Korea will be able to export hybrid generation systems based on the developed technology to emerging and developing countries and be a global leader for coal-fired power generation technology. The KIGAM and Hanil Cement seeking an answer to the question about coexistence of power generation and the environment are making the technology for the earth, the technology for a bountiful tomorrow, and the technology for empowering Korean economy. The KIGAM and Hanil Cement will make every effort together until Korea produces a new standard in the coal-fired power generation market by means of the low-carbon high-functional green cement.